I'm Andras. I'm a data scientist at Pivigo, and I'm here with Adam from HAL24K. And we're here to tell you about a project that we did together in partnership between Pivigo and HAL24K last summer. But before we go into the project, I would like to give you some background on Pivigo. So what do we do? So we do two things. We are running a data science marketplace, as well as we are a training provider. So in the marketplace, what it means is that we are working together with businesses to define data science projects for them and then match them up with the appropriate freelancers, contractors who would be the best suited for the job. So these projects are usually contract-based, they're not permanent jobs. And our role in these is to design the project together with the business and then see this project executed well within the context. We have offices in London and Berlin, but we also ran about 1/3 of our projects remotely. So what this allows us to do is to reach further beyond the UK and Germany and work with global organizations as well as people from all over the world as freelancers. So far, we have worked with more than 120 clients, ranging from small startups to multinational large corporations, as you can see in the list. We also work with nonprofit organizations and government agencies, so there's a big diversity in what sort of domains we work in and what sort of businesses we work with. And to date, we have completed about 220 projects, which are also similarly diverse, ranging from churn models or segmentation analysis to natural language processing and image analysis, as you will see. The case studies, as mentioned earlier, for some of these projects are attached to the materials of this seminar. We are also a training provider, so we are running a training program called Science to Data Science, or S2DS for short, 3 times a year. And these are 5-week training programs where the participants are researchers from an academic background with master's at PhD level, training in some quantitative discipline, typically from the natural sciences. So these participants work in teams of 3 or 4 during this 5-week period, and they work on a single project, which importantly, these are real business problems. So we are working together with real businesses who bring to us real problems that they're facing, and we design the project for it, and the teams work on it. So although this is a 5-week program, usually the outcomes are quite amazing. It's quite amazing what these people can do. And the project that we're going to talk about is such a project, and the team who was working on this is Camilla, Pascal, Tamas, and Luis, and they did all the work. Although Adam and myself acted as mentors on this project, these are the guys who designed the approaches to the solutions, they executed it and did all the work. So all the work, all the credit goes to them. And with that, I'd like to hand over to Adam to introduce HAL24K, who brought the problem to the project.
Thanks, Andras. So as Kim mentioned, I've had a long connection back to Pivigo and S2DS, and so has the company. So before we got into the details of the project, I just wanted to give a brief introduction to both. So HAL24K is a data science tech startup founded around 2014. It's based in Amsterdam, but with offices out in San Francisco, London, and Singapore. We, as a company, work in the smart city, smart infrastructure space. But one of the key things that we decided to do early on was that we recognized the need for an end-to-end data science delivery platform that facilitated everything from data ingestion through experimentation, modeling, figuring out, how are you going to solve these problems, through to deployment and putting things out at scale with graphical dashboards and other interfaces that allowed non-technical people to access that information. So in the context of doing that, what we called Dimension has been constructed and built over several years and is still under active development. And that's one of the tools that we use to accelerate our data science development. And whilst we've been doing that, we've been working in a number of spaces. Primarily, the idea was always to leverage artificial intelligence and data science and neural networks, machine learning, all of that modern tooling in a way to make the world a better place for all of us to live in. And so space where we've actively developed solutions which are in the marketplace now are working have been in water management, mobility, which includes both traffic modeling and optimization of maintenance of that traffic infrastructure, and that lends into asset management as well. So digital video tracking and recognition of problems on highways, for example, as well as modeling how you'll actually put the repair work in. So we occasionally have crossed into some of the other areas, things like you could see on this wheel, things like airports and harbors and pollution. And I think in some of the case studies you have access to as part of this webinar, you'll see some of those other projects that we've previously done, in part through STDS as research experiments that we've blended in that. And these are all areas that we see value in, but the places where we focused in the last few years have been water, mobility and asset. As part of that, the company has a number of strategic relationships and investments from some big players in some of this space, so people like Vinci Energies, Royal Haskoning DHV and Dura-Vermeer. Many of these you'll either not, they won't be necessarily be common names to you, often because many of us are unaware of the people who actually build a lot of the infrastructure that we have, but a few of them are also large multinationals that are based more on the continent than that you may be aware of them in the UK. But to quickly explain also who I am and how I got here. So I'm a lead data scientist, actually. I need to update that job titles on the slide at HAL24K. So I was the first hire into the company back in 2015. The data science team now is 9-10 people. So we've grown quite significantly over that time scale. And like I say, we're working on smart cities, smart enterprises, and delivering that out at scale to third-party providers as well as city and local government. I'm also quite passionate about communicating the power and engaging with academia and training in order to bring the skills through to feed the future of the industry as well as the business. I need to find new talent. I need to build these teams. And as part of that, I've been a Royal Society Entrepreneur in Residence for the past couple of years, in part thanks to some support and endorsement from Pivigo when I was going through the process of getting in. And I'm connected to the University of Southampton in a lot of those activities. I also am involved in charity work through a long-standing partnership with DataKind, where I volunteer in a number of different roles. And if you're just curious to find out more, you can find me on Twitter. You can see my the detailed CV on LinkedIn, or if you really want to, you can go and read my very it's been long waiting for some updates blog there at the very bottom. So that's me, and I've already alluded to some of these key areas that HAL24K is in, and the big challenges that we see what we've been tackling are the fact that we have hyper-urbanization, cities and the populations within them are growing. There are huge sustainability goals that need to be met through how you actually support large populations and how you do it efficiently and in an environmentally friendly manner. We're all aware of autonomous vehicles and the autonomous car, which is going to completely change how traffic management and infrastructure is going to come. But climate change is in here, and climate change is a huge thing that we have to tackle, and it's impacting our lives in all sorts of ways, from water supply and management through to the main topic that we're going to get to today, and that is increased risks of wildfires and the mayhem and the damage and devastation they can lead to. And on that note, I'm going to hand back to Andras to put the problem that we kind of came into Pivigo to present, to take to an S2DS team last year to do some research to see what we could do in this space.
Thank you, Adam. So this slide shows a very interesting picture of the world, with every dot representing a wildfire in the year 2019 between January and October. And when you just zoom into it on an appropriate platform, you would be quite amazed how many wildfires are actually erupting and going on around the world as we speak as well. So in the next slide, you can see that the wildfires are actually happening. It's a modern reality. Of course, there was the Australian wildfires, then Brazil wildfires were headlined in the news, and then currently Siberia is also on fire while we're in lockdown. So it is actually quite a pressing issue as well, because the number of wildfires that have been detected is on the increase in the last century, particularly in the last few decades as well. So what can we do? What do people do? How do people fight fire? Well, it turns out monitoring and prevention is the most efficient tool to handle wildfires. While wildfires are still small, it's easier to put them out, to control them. So it's key that we understand where they prop up. The technology that's been used for ages is lookout towers. So people would just look and then report if they see smoke or fire. Has been superseded with photographs in the middle of the last century, put on airplanes. But today we have actually much better sensors and infrastructure to detect fires at different ranges. So also on the ground, like smoke detectors, or in the air attached to drones. And something that's related to our topic is we also can monitor wildfires from space, from satellites. And all this data streaming from sensors needs to be processed, and then it's shared for actually raising a flag for detecting and tracking the wildfires. So on the right, you can see a snapshot of such a service, which is run by NASA, which shows live on an interactive map where wildfires are currently in the world. So there are quite a large number of wildfires running as we speak, and pretty much at all times. So the project had to start focusing somewhere, narrow down the focus to start developing a very useful tool for this. And I will hand over to Adam to explain how the project evolved.
Thanks, that's fantastic. So part of this, as I mentioned, we have connections in the company out in California, in San Francisco. In fact, how I came in and became aware of HAL24K is due to relationships I built in one of my last academic postings when I was working out in Stanford. And you would regularly, wildfires were things that happened. You would see the smoke, you would see it on the news. But the scale of it, when you actually start delving into it, and more of us are probably aware because of some of the big news items that have happened in recent years, certainly in Europe, where we're not so familiar with, certainly in the day-to-day life experience, quite the scale of what some of these problems are. So in 2018, which is the backdrop for when we were doing a lot of this work, because we did this project last summer in 2019. So 2018 was the history at the time when we were planning the project, and there were over 7,500 incidents. And there are multiple different costs. When we come to doing data science, we're always looking for, what is the value added? And to some degree, whilst $20 billion is a huge amount of money, I don't like focusing on that as being the cost, because it killed people. It devastated the environment. It burned over 6,000 square kilometers of area. And as much as there is debate about how much natural burning needs to happen in woodland, a lot of this is at a huge scale, partially because of how we've developed the landscape. So there is still, this is still partially down to how human beings have handled this stuff. And it goes beyond even that, because as a consequence of these fires, you will contaminate water supplies. So we're going to go in and look at some of the examples. So in recent years, so at the end of 2018, there was the Mendocino Complex fire. And that on its own was $257 million worth of property damage and infrastructure damage. Huge areas destroyed. But it can take 9 months for the local groundwater systems to recover from this, because the amount of ash and debris and everything else that gets filtered through, suddenly, even when the fire is out and the population returns or tries to return to normal, they suddenly are dependent upon state and government aid to ship in water. Bottled water is suddenly still being provided potentially 9 months later because of the actual environmental impact on all sorts of areas of the infrastructure. If you want to go with most expensive, you look at the counter. These are all named after the places where they started. So this costs $16.5 billion. I mean, these are huge sums of money. So any impact you can make in this, you can get insurance providers will be to some degree chewing your arm off if you can really stop this. Huge areas, there was again, it wasn't as large, so you haven't got as many square kilometers, but almost 20,000 buildings were destroyed, and in this case there were 86 civilian casualties. And so it starts to raise the question of how do you reduce the impact of wildfires. And part of the way this whole project germinated was I went to the first Wildfire Technology Innovation Summit in Sacramento, California, just over a year ago. And the concept was, here they have in California, Silicon Valley, they have Stanford, they've got Berkeley, they've got huge research institutions, they've got really smart technologists and innovators building new companies, as well as the big established behemoths. And they kind of raised the question of what happens if we actually try and bring all of these people together. So the conference was really interesting because you had everybody from firefighters who literally have been there on that front with the flames licking at them, trying to deal with this stuff, through state government, federal government, anybody who's interested. And you had people from around the world. You had people from Australia, where they've been trying to tackle this problem. You had people from Russia, from Europe. You had a huge audience, and conversations started. And this was one where it was a little bit shocking to me to discover that it was the case that the main piece of technology for how do you know when there is a fire, somebody sees smoke and somebody calls for the emergency services, which is all well and good if you're in, if the fire starts next door. But if the fire starts in the middle of a forest where there is nobody, how big does that have to get with all of that fuel before it's at a scale that somebody notices? And because of the size, again, of the landscape, you've then got to deploy resources out to try and stop it, and that still takes time. So there's all sorts of levels of innovation. One of the other pieces that was really interesting to hear was, in rebuilding afterwards, one of the things they've learned is to stop making power line poles out of wood, because they burn, and then you have to actually re-erect new poling to actually get the power back out to people. If you at least have metal pylons, they often will survive the impact. So it was literally at every level. And so whilst there, I was talking to people, and I'm an astrophysicist by training. That is my background. I spent 10 years as a researcher, so I'm used to using satellite data. And as you will have seen, that there's already space-based data being used, and one of them, the NASA tool that Andres demonstrated there, was showing you the locations of wildfires, but it's very much doing it in a absolute threshold kind of way. It's not, there's no real, as far as I know, at the time when we were originally looking at it, it wasn't really using anything machine learning. It was looking for hotspots. And how do you find hotspots from space? Well, you're looking at it with infrared effectively. So what we tapped into here because we were going to focus on California. We knew there'd been a huge problem in California and on the West Coast. So we went and found the GOES satellites, 16 and 17, are geostationary satellites. And so this helps solve our problem a little bit, because we don't have to worry about the Earth turning or moving. We're going to some degree, have a static image of the Earth, or the part of the Earth we want to look at. And it records in 16 different bands. So we have everything from the visible through the infrared. And we get images were available at a 15-minute cadence. So you get regular intervals of getting this data. So that's also really cool. And you can see here in a snapshot of what the Earth disk looks like in a number of those different wave bands. The challenge that partially comes from this data set, however, is that because it's a geostationary orbit, it's pretty far away, which means that each pixel in the image is actually 2 by 2 kilometers. So that's actually quite a large area. So a big question was, are we going to be able to see anything in this? And whilst I suspected, yes, we might be able to see a large fire, are we going to be able to, we're certainly not expecting to be able to see people's campfire gone can. That's never going to trigger this. It's not going to get hot enough in that total area. And this is kind of illustrated when you start zooming in. Here you can see the degradation in the image quality. And some of it's partially dependent upon wavelength as well, as to quite what you're able to see through the atmosphere as to the quality. But this was the question. Can we take this data, which is freely available, it's regularly sampled, it continually monitors an area, can we use this somehow and turn this into a new and innovative wildfire detector using some of the latest data techniques? And that's what we took to our team of 4 S2DSs. Now, that was what I gave them. They started using it. They had to figure out how to access the data. They had to figure out how to manage the data, and we'll get onto that in a little bit. But one of the other things they realized is they wanted to enrich it. They wanted to add extra value. So what you have here is 2 shots across the Bay Bridge coming into San Francisco, one in November of 2018 and one from October of the same year. And as many of you, I'm sure, have visited San Francisco, I can promise you this is not the fog causing the visibility problem in the November image. That is actually the smoke coming off the Mendocino Complex fire, which is actually up around Sacramento. It's not immediately proximate to San Francisco. So they had the idea of, well, we know that once fires are certainly burning, they're going to produce a load of pollutants and they're going to change the air quality. So can we find air quality monitors and measurements and use that data stream to further inform what we're going to get from the space data? And spoiler alert, the short answer is yes, it will assist and it does help. The challenge partially comes from here now, though, is that you don't have uniform, regular sampling in a spatial sense. You have spot measurements across the state. So they were able to use it in places, but obviously there are then huge gaps in the actual overall coverage. But part of the idea here was, would it prove the point that it's valuable in this sort of analysis? So this is kind of the pipeline that over the course of 4 to 5 weeks the team were able to build for us. And what you have in part is you've got the satellite images, and they're going to need to be selected. They need to be pulled down off from whatever internet source that we've got access to, and then actually transformed and cropped. So we don't want the whole image. You saw you've got the whole disk. There's no point storing all of that data all of the time. So you need to pull it down, constrain it to the region of California that we were going to be monitoring in this case. They also needed to go and actually find some labels for their data. Anybody who's done any of this machine learning and deep learning work knows that you're best off if you've got actual labels of what's going on in your data set. So what we did here was, fortunately, many of the wildfires in California have been recorded and logged on Wikipedia and other sources. So they actually built a scraping tool which would allow you to run over and extract out all the information and then do geo lookups to get approximate areas for where these fires were. So you've now got dates and times and locations of where fires are in the last 2 or 3 or 4 years, actually, I think it probably was. And then there was the air quality data that they found access to that was being made publicly available. That equally has to be sort of pulled down, any relevant metadata stored with it, and then they were storing it. They had their own storage system set up, and then from there you have to start extracting your feature sets out, and that includes the wavelengths, subcutting the images down. So we didn't just try and go with, is there a wildfire in the state of California, because odds are there probably is, and you're not getting very much information. So they were tiling over the state, and then extracting the appropriate features and the appropriate labels for, is there a fire in this zone? What's going on? How do we do this? The idea was that that feature set would then be passed through for model training and then ultimately validation. But you can equally imagine that once you've done that step, you can export that model out into you could have exported that model out into the real world, and you reuse most of this pipeline for actually pushing this into a deployment sense that just tell me, now I've just got a load of new data that's down. Is there a wildfire? If so, where do you think it is? Now alert me. So one of the really cool things that they actually did whilst they were working on this was, and this is where I often have found some real value from us as the company sponsor of the projects, is that we've always tried to give interesting problems, but where some of the business value actually comes out is in how they've solved them. So one of the example pieces here was the team were working in parallel on a number of different techniques, and there's obviously a huge amount of data. When you're talking about 16 wavebands every 15 minutes for the entire disk of the Earth over several years, that's a huge amount of data. There was no way you were going to pull down and store all of that data live unless you've got a pretty big server, which I promise you we did not give them. So they did pull down in total about 6 terabytes of data, but you don't want to double up, you don't want to waste. So one of the pieces they actually wrote in their pipeline was actually their own caching solution for checking, has anybody else on the team actually already gone and pulled down the relevant data here? And do we have it stored? And that way they didn't reduplicate effort. And that's the sort of tooling that suddenly for us, if we're then taking this sort of project and putting it actually out into our product, that's the sort of thing that we can lift out and we can put in quite straightforwardly and go and deliver really fast value back into our business. So thousands of sample frames were being pulled out, and this was developed over the course of the program, 4 or 5 weeks. It was really interesting actually, because I was talking to members of the team, and they were reflecting how when they started this project, they were so I arrived on the first day of the program and gave them the briefing, and said, okay, this is what you want to do, this is how we're going to set it up. And in their discussions, they were like, OMG, how on earth are we going to do this? This is crazy, this is huge, this isn't, this is years of academics equivalent work. And with nudging, Andras was providing day-to-day technical support. They were checking in with our data science team for advice and suggestions in places, and I was trying to manage and maintain that overview and keep them on track. But they were able to build this, and they had a functioning full end-to-end pipeline for model training and validation by the end of the program. Now, the big question, of course, is, did it work? So they developed a number of different models actually in parallel, in part because they didn't know what would work. And this is always crucial, I found, certainly in this space, is the reason it's called data science for a reason. There's a load of experimentation involved. So they started off with a pretty simple model of a decision tree. Someone else was working on, well, okay, let's scale that up in case we need more weak learners in order to get a better forecast. So they went and they started constructing random forests as well there. And also convolutional neural nets. These are the big things that we've all seen doing amazing things, whether it's started out as YouTube identifying cats in videos, through to some of the really advanced image detection algorithms that we see in live computer vision and monitoring. But it was another component. It's like, okay, well, we'll test this too. And in the timescale they had all of them trained up, they had all of them running. and they all were working at about 85% accuracy. The interesting thing, beyond the fact they were hitting the same scores, were they weren't necessarily all accurate in exactly the same ways. So there was still power here in that they were able to combine the outputs of these into a combined estimation in places. So they used subsets of the models that they had to actually layer the inference together to come up with a better overall estimate of what they thought was happening. And this is, you know, it's a simple line graph to some degrees, but this is when they took the average of a load of predictions over time, over both time and some of that modeling. They went and they looked at the Mendocino Complex fire, and this was their test case because this was the biggest fire. You know, if you can't detect this, you're not going to detect anything. So this was that starting point to the proof of principle. And you can see in red, that is the primary time Mendocino was burning. And you can see there was an increase in the overall probability. Now, none of this had been, you know, this is no calibration's been done here, no thresholding. So quite where you want to set 0, you know, no fire and fire, because obviously it's a very Boolean piece. But the great thing here is you can see that it does significantly go from before of something like 0.55 to 0.6 average. It peaks up at over 0.9, and then it decays back down again. And I'll come back to why that decay might have happened. And some of you might even have your ideas already, but you can see it drops back down. So in some respects, this is the shot that kind of indicates the concept is worth investigating. There is value in doing this potentially. The concept is sound. You can get inference out from this data for what you want. And this is then what they started doing. So you can just turn it into, okay, if we now just set a fixed threshold, you can kind of just start coloring in and highlighting pixels of, oh, there's a high probability of a fire here. And this is what you're seeing on the left. However, what the team realized is actually they could start combining some of the inferences they had in a more Bayesian context of saying, okay, well, can we actually turn this rather than just into an on and an off? Can we actually come up with a better probabilistic model, which will say these are the risk, the areas where we think fires are most likely happening? Now, don't forget, remember, this is still building primarily off pixels that have a 2 by 2 kilometer size. So, you know, to some degree, we expect we should be able to find big fires, but you're not going to expect to find everything. And when you start, this is that data. This is that equivalent data. It's not projected in exactly the same way, so don't tilt your head too much trying to figure it out. But this is that raw data that's going in to figuring this stuff out. And when you actually then go and look, we can compare it to the NASA firms data that we saw, which was, is very much on fixed thresholding. And what you'll notice is, so the big blue blob in the top left, that is the Mendocino Complex fire. That's up around Sacramento. It was 2 different regions burning all at the same time. And you can kind of see from the firm's data, there are equivalent clusters of hotspots around there. So it looks like we found that. We've seen the pieces down in the lower right certainly seem to be picked up. And you can see from Wikipedia also where the detection elements were. And they're doing pretty well. This model is actually doing things. Now, the interesting thing in part is that some right at the top of the state, you can see them as kind of the big red square in the top left of the firm's data. That wasn't picked up. But we don't know actually how big that was, how far into burning, and so on and so forth. So it's not perfect. Nobody was expecting it to be perfect, but it's working. It is finding things, and it looks to be finding fire in the right sort of place. So I'm going to go back a slide actually. So one of the things that we thought on the back of this is we've got a problem actually in our labeling. And if you think about it, this might actually explain why that slope dropped off for the Mendocino Complex. Those Wikipedia markings of fires have been what we've been using as labels. But you're using effectively the ignition site and some radius circle is defining this is a region on fire. And when a fire burns, it doesn't stay where it starts, it moves. And so what you actually have is a dynamic fire front. you have regions on fire. And so actually our labeling as a fire evolves is probably getting more and more wrong as it goes. So one of the things that we realized is that what you'd actually possibly need to start doing is moving a load of that data through into a better labeling engine to get better labels, and you could actually probably re-engineer a load of the models that have already been then constructed to get much better overall estimations at the end. And you might be able to, and we've already seen it, that the estimations are on pixels, and so you'd actually might start seeing fire boundaries coming out, and you see where the real burn is happening. There's other areas where you could start exploring, and we were in discussions, but we only had so much time to work on the project. At the moment, all of the data was being used as independent measurements, so nobody was looking at, if I saw a fire yesterday, the odds of there still being a fire again today should be higher, and it should maybe have slightly moved. None of that time inference was being combined. You can start to think about the fact you might want to use short-term models with this sort of thing, and actually almost take in the time series of the images. And these were all really good discussions that we actually had with the team. So you heard about them at the beginning. So you can see myself pre-beard in the top left as the business and overall project manager mentor. Andras is there again as the technical mentor who helped them through the project. But Camilla and Thomas and Pascal and Luis, they're the ones who were the driving force behind doing this. So you can see them all in their lovely HAL24K orange, you can tell it's a Dutch company, t-shirts, ready for their mid-session presentation. But the insights that they gleaned from doing the work and the ideas for where it could be taken afterwards really show the power, I think, in exposing these groups of people who want to make the transition into data science to real business problems, because they come in with smart ideas and you expose them to that concept and the problem, and you will get all sorts of stuff out. Like I said, everything from an image caching solution through to how to actually get the overall problem to work. And if you only wanted one slide to take away, this is kind of the summary slide of all of that. You can see how it goes from satellite data and Wikipedia point labels to a Bayesian estimate of spatial distribution of fires across the state, and to actual probability risks of fires kicking off as a function of time. And all I want to say is, again, a big thank you to the team. Thank you to the team at Pivigo and STDS for facilitating these programs. I mean, I'm not going to say that we didn't put effort in. We definitely did on trying to develop the projects and managing and running it, but it's all done in partnership, and we couldn't all do it if we didn't bring all this stuff together. And on that note, I'm just going to say thank you.